All right, so we continue off our discussion of lecture series number 7, and I guess we've gotten to a stage where we have a fairly good enough understanding of this whole notion of machine learning. Simply put, any machine learning problem could be viewed as being a mathematical function, y, which is equal to fx, obviously, and your x would be the input data, specifically it would be the attributes associated with the input data that you're working with, and the input data will actually determine the outcome of the y, right? And by the way, we are loosely describing machine learning from this perspective. You will notice very, very soon that there are different things that come into play depending on the specific machine learning technique that you are exploiting at that point in time. So issues to do with the fact that the data that you're working with would need to be labeled, for instance, are extremely important for supervised machine learning techniques, right? The other interesting thing that we highlighted was the fact that in fact the x could be viewed as being composed of so-called independent variables, and the y would be a dependent variable. Great. So we're just going to walk through some examples here of the traditional machine learning techniques. And our focus really here is just linear regression, I guess, classification and clustering. But our discussion of these different machine learning techniques will take the shape and form of those broad machine learning categories, right? So supervised learning, unsupervised learning, and semi-supervised or reinforcement learning, right? So it turns out that one of the common machine learning problems would typically involve some aspect of supervised learning, right? It's rarely the case that you'd have or you'd end up working on a problem that's similar to what Knox did, where you don't know what it is you're looking for or you're interested in is to try and identify patterns. For the most part, you typically end up solving a problem where you already know what it is you're looking for. So it could be that you're interested in predicting a future numeric value. A word example here would be maybe we would be interested in predicting the salary of a junior developer in 2025, for instance, in Zambia, right? We already know what we are trying to work towards, right? It's predicting a numeric value, and so all we'd have to do is identify which x's would have to use as input, right? So things like qualifications, I suppose, skills that person has, the years of experience that they have, or something, right? Well, what you immediately appreciate here is the fact that when it comes to supervised learning, what's extremely important is that the x's, the input data that you're working with, needs to be labeled, right? It needs to be labeled because what you are doing is you are training an estimator by feeding it labeled data, right? So you would examples of labels here would be, let's say, data labels associated with learning outcomes, our ICT 1110 example. Your data would have to be labeled in such a way that you have a training set that has the demographic details for each of the students, right? And the exam scores that they got, or the grade that they got. And if you think about this for a second, right? What you would be implicitly doing here is you're saying you're using historical data. This would be results from last year, for instance, to train this model so that you're able to predict future values, right? So key thing here is the data needs to be labeled, and the labeling is nothing more than or will take the shape and form of you having a y and an x. So you'd need to have you'd need to have a data set that has values for y and values for x. All right. So the labels here, what we're referring to as the labels here is the result of the estimate or the algorithm itself. This would be the Y, right? Because here the assumption you're making is that you already have the X, so you'd need to ensure that your data set is labeled with the corresponding Y's essentially. And so what you do is you use the labels and the X's, so the Y and the X's, right? The data attributes and the labels to train the estimate or the algorithm. Essentially, you would be implicitly telling it to say every time you look at this combination of X's, the outcome is going to be this Y, right? And once you expose the estimator to different variations of X's and Y's, then it will be able to better predict what sort of Y would result given an unknown X, right? So that process itself, where you are exposing this estimator to different variations of X's and corresponding Y's, is what's called training, right? So you'd be training your estimator. And really the goal for supervised machine learning is you are almost always interested in predicting a value, right? So it could be a specific quantity or a specific outcome in the case of classification, right? What will be the exchange rate next year in January, right? Rather than having human beings do that, you just look at the historical trends and then you predict what value it's going to be in January. And of course, that would be complex, I suppose. I don't know. Maybe we'd have to involve a domain expert here from an economist, someone who has intimate knowledge of what sort of factors influence the exchange rate. Right. And so obviously something else that comes into play when it comes to supervised learning, and in fact most machine learning techniques, is at some stage you would have to actually measure the relative success of you predicting the value, right? And so things like accuracy will come into play very, very soon. And we have a discussion about this. All right. So if you think about supervised machine learning here, I kept on mentioning that it can either be a classification type problem where you're predicting a category, or it could be a quantity, in which case you're predicting an actual value, right? So when you're predicting an fx given an input x, if the fx if the problem involves classifying a category, then that would be referred to as a classification type problem, right? So whenever the y that you are working with as part of your function is a category, so pass fail, male, female, then that is a classification problem. If your fx though, or the y, is a numeric value, or if it's a continuous value, then that would be a regression type problem, a linear regression in this case, right? So you notice here, supervised learning can be further subcategorized into classification and linear regression or regression, right? And fundamental difference being that in this case, what you're predicting is a continuous numeric value, and in this case, what you're predicting is a categorical value, right? Now, this categorical value, if you remember Stevenson's classification of data here, we introduced this whole notion of different types of categorical variables, right? I don't know if people remember here. So things like ordinal values, for instance. All right. So I thought now would be a good time, just again, seeing as we've just broken up supervised learning into these two, just going to go through some really wild examples, right? So common thing that you probably find in literature is people wanting to predict things that would normally struggle with a society, right? So you find a lot of literature that is linked to educational learning outcomes, for instance. So this paper, a classic, by the way, I wouldn't say it's a classic, but pretty useful because the context is somewhat similar to Zambia, right? This was done in Kenya. I know this person because we used to sit in the same lab, by the way. So in this particular paper, what Mgala and Boko do is they really were trying to work towards trying to identify what sort of intervention would be required, what sort of intervention students would have to be exposed to. So they broke up their FX or their Y was a classification type problem where they were interested in trying to predict whether a student would require high intervention or low intervention, right? So a student requiring high intervention is more likely to fail. A student requiring low intervention is less likely to fail, right? And if you read up on this paper, what you notice is that the stream of X's that they were playing around with here incorporated so many different things. So you have demographic details here. You have attributes associated with test scores, attributes associated with student motivation and study time. Now, if you read up the paper and if you read up the paper itself, what you appreciate is that some of these X's are a bit questionable, right? Questionable in the sense that some of them are more subjective, right? So think about this for a second. You go out there and you go and ask a grade 5 or a grade 6 who is about to write grade 7 exams, right? How much time do you spend studying this particular course, right? I don't know if that would be a fair way of trying to identify this variable. But anyways, key thing here is that this is a classification problem. Supervised learning, but specifically it's a classification problem. And when you read up in this paper, what you realize is that Mgala probably went through a tedious process of manually labeling this data, right, to come up with a training set, or to come up with the labels. All right, so classification problem. Another common problem domain that people normally exploit is so-called document classification, right? What these people from Pennsylvania State University did in this paper is they were interested in trying to classify documents as either being books, presentation slides, thesis, or ETDs, or papers, or maybe resumes, right? And so what they did was they took a really clever approach where they identified X's or input values as being broadly clustered into file-specific attributes, text-specific attributes, and section-specific attributes. So the idea behind what they were doing is that if you look at a document, there are certain markers that you can use to determine whether that particular document is going to be a book, slides, or a resume, right? Again, the labeling here was manually done, right? It's as easy as identifying people to help with the labeling process, and then they go through a tedious process of just scanning through the document and identifying to say this is a book, this is a thesis, this is a resume, right? Again, if you look at this, the classic classification problem, right? What you soon appreciate once we look at specification in great depth is that it's a specific type of classification problem. This is what's referred to as a multi-class classification problem. This is classic binary classification because you're predicting, what you're interested in predicting is either of two values, high intervention or low intervention. And this could be viewed as being binary, right? 1, 0. 1 is high, 0 is low, right? This is a multi-class classification problem. It gets even better. There are certain problems that are so-called multi-label classification problems. So these would be classification problems where your Y can be more than one, can have more than one solution, right? So if this is a bad example here, but if let's say if one of the Y's wanted to predict is whether this would be, sure, it's book, slides, thesis, paper, resume, but is it also peer reviewed, right? In which case, you know that you'd have, in each permutation, you could have more than one Y. So if it's a book, that book could be peer reviewed, right? If it's a paper, that paper could be peer reviewed. Obviously, slides likely not to be peer reviewed, right? So that would be a multi-label classification problem. But fundamentally, these are all these are all supervised machine learning techniques, really, right? Another classic paper that we looked at last year, these people were trying to figure out if they could identify at-risk students by looking at the way that they interact with Moodle, right? Again, by looking at the type of prediction that these people are interested in, you can easily see that's a classification problem. So what they were fundamentally interested in this paper is to identify if a student is at risk of failing. So it's either the student will be at risk or the student will not be at risk. So classic classification problem, specifically, it's a binary classification, right? At risk, not at risk. Common examples that I'm sure most of us have come across here is email, right? And this happens over and over again. I do hope I can do this. This happens a lot. Everybody probably does come across at some point. At one point or the other. Let's see here. Where's my spam folder? Wow. Do I not have a spam? More. Thank you. Right. At some point, I'm sure you've come across. You've received spam, right? Can be irritating. I guess it's effective sometimes for people that don't understand how computers work. But most important thing here is that in certain instances, you will receive an important email that will be classified as spam. In which case, you would have to go into the spam folder. And this is a bad example. I wouldn't want to. There's nothing in here that stinks of being a valid email. So maybe if I go to my personal email mailbox, maybe that would be classic. It's where I normally have messages that are destined to be not spam but are classified as spam. So if I can, wow, there we go, spam. Come on. Oh, wow. Okay. Maybe. It's quite strange. I thought there was no power, but there is power. Great. Okay. Anyways, but what I was wanting to get at here is that in the event that something has been classified as being spam, but it's not spam, what you normally do is you go to your spam folder and you explicitly tell your email client, I guess in this case, or the email service that you're using, to say this is not spam, right? In which case you're actually retraining the model, right? So the model in this case has already been trained to say when you look at, and by the way, this typically will make use of text in the email, right? The number of things that are used here. It could be the sender, right? You look at the sender, you look at the text, you look at the subject here to try and figure out whether or not this thing is going to be spam or not, right? So it's an automatic classification. Anyways, classic example of supervised machine learning is classification, because you're interested in classifying whether it's spam or not spam, right? And also it's binary classification here, because an email can either be classified as spam or not spam. It can't be both. All right. a classic example that we normally use, we've traditionally used as part of 5741 is to use this dataset, JCTR dataset, to try and see if we can make predictions of the basic needs baskets into the future, right? And granted, our models are normally simplistic in nature. The implementation is quite simple, really. We just look at usually our fx is a very simple linear function where we just look at the historical trends. But if we could potentially make this more reliable by taking into account, I guess, other x's or other variables, like maybe the exchange rates for currencies that we normally use in Zambia. So the rand, for instance, and the US dollar rate. Right, and perhaps if we were to engage an expert or an economist, they'd be able to identify additional x's that we could use to come up with a more accurate prediction of the fx for the basic need basket, right? But this is a supervised machine learning, and specifically she's regression, right? All right, but it's not always the case that it's not always the case that you'd know exactly what it is you're interested in predicting. It might be the case that you don't know what it is, but you just want to make sense out of the data. You're interested in patterns, in which case you'd be working with the classic unsupervised machine learning, right? This is where the clusters that Knox was talking about last week come into play here. So by using estimators that are specific to unsupervised machine learning, such as clustering techniques, for instance, and K-means, by the way, happens to be one of the most widely used, you'd be able to identify what sort of patterns exist within the data. And it would be up to you to take that additional step, that next step, to try and describe what those clusters represent. Right? What the estimator will tell you is to say, based on the data that you fed me, I think that these observations, the observations that I have here are somewhat related to each other, right? These observations I've clustered here would be related to each other, right? These observations here are related to each other as well. So the estimator will not know what sort of relationship might exist. It will just tell you to say these are related somehow, right? So it will be up to you to either do it yourself or engage experts to identify what attributes make these related to each other, right? But fundamentally, you would have identified what sort of pattern exists in there. So you're not predicting any specific value per se. The goal is just to identify patterns that exist. And you probably have already appreciated the fact that because you're not interested in predicting a specific X, there's no point in labeling the data. Right? So no need to label the data, because all you're interested in is identifying what sort of patterns exist in the data. Then also, you don't need to perform any sort of training, obviously, because the training is a process you undergo to associate x's to the y, right? And that y is equal to fx function. And for the most part, most of the evaluation that takes place, right? If you remember my explanation of these patterns that I had here, right? I said the estimators will be able to identify the patterns that exist, but the process you go through by trying to figure out what these patterns mean would involve some aspect of human effort, because you are engaging human beings, right? It's the evaluation is qualitative in nature. It will be descriptive somehow, right? In the case of Knox, it would be, these clusters are associated with dormant accounts. These clustered here are associated with accounts that are rarely credited, right? So that sort of evaluation would be qualitative in nature. And usually most qualitative techniques would typically be subjective, because our interpretation of things in life is not almost always the same. And a common workaround for that is, in the case of subjective measures, you typically would want to involve more than one person evaluating the same thing. So if you are wanting to describe what these patterns represent or mean, you would have more than one person describe this, and then you compare the description from the different people that are participating in that evaluation process. And also, an important thing which will probably come up once we discuss clustering, I hope I won't forget this, but you typically use an odd number of people, and really there are different sort of approaches taken here. So you use an odd number of people and you say the majority wins, right? So if you're working with 3 people evaluating the same thing, if 2 people end up suggesting that the interpretation of this cluster is, let's say, A, then you go with the 2, right? Another approach is you could say you want to make sure that the description is unanimous, right? You don't want to leave any room for errors, in which case you'd have people redo the evaluation if there's sort of like a discrepancy or a difference in the way that the evaluation outcome happens to manifest itself. But key thing here is that you typically make use of subjective measures. And again, I just want to draw attention to Nock's presentation where he brought up, I asked him a question to say, how did he arrive at the 8 clusters, if you remember? And he mentioned that he used the so-called elbow technique, right? So the elbow technique would be a technique that allows you to sort of like come up with a plot of the resulting clusters, right? And using the elbow technique, you'll be able to identify how many clusters exist or can be associated with your data set, right? So the process of identifying where the elbow lies on the curve is subjective, because a human being would have to look at the curve and say, oh, the elbow actually lies here, right? Granted, there are more objective measures that you can incorporate into clustering. So a classic example here, I think some of us are working on the Go Zambia job, right, portal, where we are wanting to identify what sort of patterns exist there, right? There's no need for labels there. All we have to do is identify the patterns and be able to display the patterns. But also, other way of looking at this problem here is you could look at this. There are some of you that are working on, I guess, supervised machine learning type problems that are associated with this data set. But I just use this because I think there's a problem that is that takes an unsupervised machine learning sort of like approach, right? Where we're interested in finding out what sort of patterns exist in the data set. Another area where you'd end up applying unsupervised learning is when you're working with massive amounts of data, right? So this image is just showing the Union catalog, which collects, or it has dissertations from around the world, right? So if you're interested in trying to make sense out of that sort of data set, and you've not worked on that data set as well, you are better off using an unsupervised machine learning approach, and you'll be able to notice that interesting patterns would be identified from the data set. But besides supervised machine learning and unsupervised machine learning, you have so-called semi-supervised machine learning, or so-called reinforcement learning, where you'd be using a combination of both supervised and unsupervised machine learning techniques, right? And you typically use unsupervised machine learning techniques to try and improve on the supervised machine learning algorithms. Usually it's in instances where you have insufficient data, for instance, right? So if you have fewer labeled data sets, you can combine aspects of unsupervised machine learning to reinforce the whole process. All right, just to mention that our discussion is just going to look at the more traditional approach. We are going to focus on regression, classification, and clustering, essentially. And these 3 approaches should be sufficient to get us started in the event that you're one of those people who is interested or wanting to work on this sort of problem next year as part of your research. But before we wrap this up, I guess would be nice to look at some obvious examples that we've probably come across and things that maybe you might not have been aware of. I mean, you see them, but maybe you wouldn't necessarily know that this could be viewed as a machine learning type problem, right? I'll just go through some things that maybe all of us, if not most of us, have experienced at some point or the other. Now, if you're like me, you probably have friends on Facebook that will sometimes post in a language other than English, right? In which case, Facebook automatically, I guess, translate. It will automatically translate. It will automatically attempt to translate that piece of text into English, obviously, right? It's kind of interesting, really. If you, I don't know how many of you understand Chewa here, but this piece of text here, kodi kusiyana kwa mau awili awa nyanja and Chewa kulibwanji. So what this person is trying to do is he's asking, right? He was asking what the fundamental difference between Nyanja and Chewa is. Now, if you look at the translation here, right, it has really very little to do with the piece of text, right? So the translation, the English translation here is tax difference in mau awili and that and that. This is ridiculous, really. This was supposed to be a 1, right? And think about this for a second, right? And by the way, some languages, the translation of certain languages is on point, right? It's like in orders of maybe 80% or something. These are what Zola referred to in that talk. Zola referred to as high resource languages. If you remember, he kept on, I think he was writing on the low resource language argument, right? So these are languages that are not represented on the internet, right? You have very little text in Nyanja on the internet. But the thing here is, right, what I'm trying to get at here is that this translation here could be viewed as being, I guess, a supervised learning type problem, right? I don't know if you can see this. It's supervised learning because it's dependent on what sort of data has already been, what sort of data has already been transcribed. So I do this a lot myself, right? So occasionally I go to Google Translate and I help. I help, of course, when when I'm too tired to do something constructive, right? I help, and there are tools that you can use. This is not exactly one of those tools that you use, but I think there should be a part where you, is it contribute or translate? Let's see, document, nope. Is it called contribute or something? There are a number of contribute. Google Translate, right? Where you get to translate. Yeah, but I did. Or maybe I had to go to the community tab here, right? I think I had to go here, community, where you get to help improve the way Google works, right? I didn't know there was. I didn't know we're changing this site. It's a bit weird here. That's weird. Anyways, bottom line here is that I'm veering off here. I'm veering off the beaten path, but bottom line is the FX here would be the translation to the language, right? And the X could be viewed as being composed of different aspects here. Number one, it would be the text representation of the text you want to represent itself, right? And also the input that comes in, right? So if you look at each translation on Facebook, will typically have an option where you can rate. And I do hope that you guys rate these things. It turns out that when you're rating, you're teaching. Implicitly, you're teaching behind the scenes, right? You're teaching the estimators behind the scenes. It's relative performance, right? In the process, with as more input is getting through to it, it gets to improve, right? So this could be viewed as a classification type problem, essentially. All right. I know this is horrible. This thinks that this is Swahili when it's actually Chewa, right? Interesting enough, this is not just Chewa. It's a mesh of different things here. Like there's and here, which is English, and which is what makes it extremely difficult, I guess, to come up with a very effective model that's able to translate languages like Chewa, Bemba, Silozi, Tonga. All right. I do not know if you've experienced Smart Compose yourselves. I love it myself. Every time I'm on Google and I'm wanting to compose an email, my mailbox, right? When I log into my mailbox, it's been personalized to a certain extent that Google knows that I almost always oh wow, this is weird. I thought I would have a Smart Compose here best. What? This is weird. In almost all instances, when I'm writing an email, right? When I'm responding to an email, there is always a part where Smart Compose comes at play, and I get to let me see if I can respond to an email here. Let me just see if I can. I don't know why we've started discussing. Shit. Anyway, so this is it. For some weird reason, doesn't want to work right now. But the way Smart Compose works is, and it's integrated within a number of Google applications. So it's not just Gmail. You also find Smart Compose in Google Docs as well. So if you look at this image here, this is from Google Docs, right? So when I was typing here, you notice that there's like a sort of like autocomplete feature where what's happening is Smart Compose is actually determining the next, it's predicting the next word that is going to come after the one I'm typing. So using a combination, right? It knows that because this is in English, it knows that the way the English language grammar is in such a way that it's likely that the word of comes after combination, right? So we're predicting the next word. Classic example of supervised machine learning here. These days, actually, you even have examples in Android as well. I don't know if people have been looking up some of these popular tools. I get curious myself. If you've been following up what's happening in the dating app scene, specifically Tinder, right? I guess one of these dating apps that has literally taken the world at storm here, probably have one of the largest market shares here. But the interesting thing with Tinder here is that they've incorporated a new technique, right? That allows you to verify your account, right? So your account will typically have a tick at the end, right? It's always nice to experiment with these things. Hope I'm logged on. Here we go. So what I mean is, if you log into this app, you notice that there's a grayed out tick here. What this means is that my profile, for instance, hasn't necessarily been verified. So for me to verify this thing, right, I would have to tick this, and then it turns out that the X's that they're using are really interesting X's here, right? And by the way, there's a nice write-up on their blog. So if you go on their blog, you notice that they use geometric features, and I think this is best done using, oh, there we go. This is probably best done using a mobile application. But the way it works here is that once you click the verify button, they use geometric features associated with, one of the requirements is you take a photo using different poses, right? So different angles of your smartphone, right? So they're extracting features and try to match those features with the images that you already have uploaded onto your profile, right? Classic example of supervised machine learning, right? Brilliant stuff going on here. Also, I think I forgot to include this, but So the labels here, by the way, would be the geometric features, right? Geometric features here in the face, and then also the geometric features associated with the pose, so the pose geometries. So they will tell you, the model that they've come up with will tell you pose in this sort of way. And so it will be able to detect whether or not you are actually posing the way you've been instructed to pose. If you think about this for a second here, one of the things they're trying to weed out here are bots. Right? It's human nature. There are people that would want to take advantage of this. I mean, it's quite easy for you to come up with an automated profile with a fake photo, for instance, right? So the question is, how do we verify that this is actually a human being and not a bot, right? Which is interesting here. It raises interesting questions like, I don't know if people remember that this person does not exist. What are the odds that we can make use of some of these automatically generated emails and maybe be able to, this would have been really wonderful thing to do, right? If we had time, try and see if we could come up with an implementation, right? Some very basic, primitive application that automatically creates profiles by making use of these automatically generated images. This person does not exist, right? That would be nice, although it would be even nicer if we could generate photos of black people here. But anyways, I digress. A while back also, I don't think I included Dropbox here, but a while back, Dropbox wrote or blog. They wrote on their blog. They wrote on their blog machine learning. They wrote on their blog about how they. There we go. So sometime last year, right? They wrote about how they were using machine learning to try and predict what sort of files you'd want to incorporate next. And really, if you think about this, you find these different things embedded within most of these commonly used applications. For instance, if you use Google Drive a lot, what you notice is that Google Drive has, and I don't know if this is just specific to. Excuse me, if it's specific to the Drive mobile application, but on the Drive mobile application, there's what they call the priority inbox, right? I think it's there, right? So this looks at the sort of interaction that you tend to have with files in your Dropbox, and then it's able to predict which sort of files to associate to this priority box, right? Which is pretty interesting in my opinion, anyway. But anyway, interesting stuff. The golden thread in all of this is, in all of these examples I've been looking at, you're dealing with massive amounts of data. If you're wanting to make sense out of massive amounts of data, you need smart ways or techniques that employ smart techniques for you to make sense out of what's happening, right? Anyway, and I also thought we'd just briefly look at some random examples from the talks that have been given here, that were given as part of the seminar series. Some of them explicitly did mention that we're using machine learning. So Francis, if you remember, walked us through how they were able to identify 4-MUMs, right? By looking at features associated with 4-MUM images, right? Classic supervised machine learning, why he needed a labeled data set, if you remember, right? Using different image orientations for these 4-MUMs. NS didn't really explicitly state that they were using machine learning techniques, but some of the problems that he mentioned, right? The problems of trying to being overly dependent on human beings to actually identify what sort of problems associated with scans. You can easily carve this out into a supervised machine learning type problem where you build a model which is exposed to different variations of images, and you tell it to say, if you look at a scan, if a scan looks like this, then it's tuberculosis. If a chest scan is like this, then it's likely the case that this person has a renal problem or something of that nature, right? Key thing here is this could be carved out as a supervised machine learning type problem, right? Well, perhaps clustering as well. If you remember, one of the issues NS cited was that most of the data that they have is not digitized. So think about this for a second. If they got to a stage where they were in a position to digitize the medical records that they have, for them to be able to make sense out of the swaths of data that they have, they would have to employ some sort of unsupervised technique, right? To be able to isolate related medical scans together. Yeah. We had Milimo give a talk specific to the telecommunications sector. Most of what she spoke about here was centered around them analyzing the data from the perspective of sales and marketing, right? When it comes to marketing, you can easily come up with, you can easily take advantage of clustering techniques to initiate more targeted marketing interventions. Think about this for a second. How do you think they're able to identify, or they're able to come up with those different packages, right? When you're wanting to buy data, for instance, one of the things they'll say is, you have the option to go for the 10 minutes till midnight, or lock on Nilak or something. And I'm reading up my MTN packages here. For you to be able to do that, you need to build a profile of your. You need to be able to build a profile of your customer base, and you cannot manually build a profile of your customer base if your customer base is, let's say, in the orders of millions, right? Last time I checked, I think most of these mobile service providers, I think MTN is probably has the largest market share, and I think they're probably above 5 million. I think, if my memory serves me right. Last year we had somebody give a talk. I do remember this. If I can just check, I guess. If I can just check this, let me just see if I can find what I'm looking for. Bear with me. This thing. All right, if I can get to last year's cause. Sorry about that. We were told that and I hope I have Andrea's talk somewhere. Andrea, I should have it, I guess. There we go, I have it. So it was in my downloads folder, actually. I haven't formatted my computer this year. So market share, subscribers. Come on, no subscriber. Anyway, I almost actually thought that wow, this is weird. I'll close that just because I've configured my Oculus in such a way that it takes up a lot of memory. But also, let's see, Zicta indicators. Also, Zicta compiles these things. And I want to wrap this in here because, there we go, indicators. I want this to make sense, right? This whole notion of when you would want to take advantage of clustering techniques and when you'd want to take advantage of, let's say, supervised machine learning techniques. Right, so if we go to is it network coverage? I guess, I don't know. I'm looking for market share here, but volume statistics, indicators, pricing. What the hell? Volume statistics, employment. It should be network coverage, I guess. I actually thought that they actually kept track of. This is stupid. There we go. No, this is for Zamtel, I guess. I don't know. Maybe ICTU indicators. Anyway, that's sad. I thought this stuff would be there, readily available. And Zicta has done a really horrible job of they actually do a horrible job of doing this. Anyway, I guess we can use this as an indicator. I mean, if we currently have a total of 9 million mobile internet users, right? And this is mobile internet users, but I was trying to point at the fact that a typical mobile service provider like MTN, for instance, will have a lot of subscribers, right? A lot of subscribers. And if you have a lot of subscribers and you're interested in coming up with a targeted intervention, for instance, a marketing targeted intervention, it becomes a bit tricky for you to manually do this, right? You would have to, you'd have to use some sort of automated technique here, right? Ooh, interesting to see someone using Oracle here. That's nice. Connecting to an Oracle database clearly. And by the way, I think this is this SQL Connect? What is this tool? I'm veering off the two here, but I wish I could find the numbers here. But bottom line is it's massive numbers that you're dealing with, millions, right? I wouldn't be surprised. Let me see here. MTN Zambia customer base. Let's see if we can look this up. Boom, there we go. So as of 20, if you look at this, this is interesting. And of course, and it's like 5 years ago, but okay, this is good. I'm going to work with the 2018 one from Daily Mail. I'll ignore this from Zicta, although in an ideal case here from an academic standpoint would go with Zicta, but we want to just, this is an approximate thing we're looking for, so we're just going to go with the most recent hit here, which is Jesus, it's gone now. Jesus, I hope this thing is still recording. I do apologize. My goodness. Why in the fuck is this happening? Jesus. I need to close some of these things because they're eating up a lot of my memory, and I know this is one of the things doing that. And Chrome as well. But so what I was saying is we'll just go with the 2018 one because it's 2 years ago as opposed to the Zicta one. This Zicta hit was from 5 years ago, so 2015. So if you notice this, right, if you notice from this breakdown here, that what they're saying is looking at this mobile subscriber base of 13 million, MTN at this point in time had MTN had 44%, right? So 44% essentially 0.44 of 13,438, 539, 44% of 13,438,539 subscribers. So MTN roughly, right? We expect MTN to have over 6 million subscribers, right? So if you're a subscriber, if you're a mobile service provider like MTN, Zambia, and you're working at that sort of scale, for you to come up with reliable targeted intervention, you'd have to make use of, obviously, clustering techniques, right? You would have to do that. Of course, in certain rare instances, not rare, but in certain instances, you might also be wanting to come up with prediction models that are going to predict a specific outcome, right? And I guess if I was it's getting cold, switch on the heater. If I was part of a team that worked for these mobile service providers, obviously, one of the things, and I'm sure they do this, one of the things I would do is for postpaid subscribers, which make up a massive amount of revenue, right? I would build profiles, specific profiles for postpaid subscribers to try and predict how much money can be made from them, right? Interesting stuff. But anyway, Most of this is centered around sales and marketing, right, in this particular sector. Just brought back a lot of memories. I used to do a lot of this in my previous life when I worked for Airtel. It was really interesting, although at the time we used very basic and primitive techniques here, right? There was no machine learning of any sort, so just manual queries. And I think this is what Milimo said they do as well at Zamtel. So they don't really use any sophisticated machine learning techniques. Right, and then we had a team from Siders that, again, they don't use any sort of machine learning techniques, but based on what they presented, you notice that you can easily build these models by using machine learning, right? Specifically supervised machine learning. So you can be able to better predict who is more likely to default on their medication. If somebody's on ART, they already have a profile of people that are on ART treatment. And so you can identify markers or X's that can better predict who is more likely to default, in which case you introduce an intervention. You call, you SMS those people, right? We had Friday give a talk based on his dissertation, right? And I want to draw attention to the ANPR component of his solution, his proposed solution, the automatic number plate recognition component. He took an approach where he used optical character recognition, right? Where you'll be able to extract the number plate associated with each vehicle once an image of that number plate was taken. But another way of looking at this is, instead of using OCR, what he could have done is he could have just used machine learning, where the X would be the image that he's taking, right? What would be interesting here is to try and see, and I think we did reach out to him to find out if he could share the data set. What would have been interesting, what would be interesting is to see if the performance would be better if it would be better if we took an image classification type approach as opposed to using classic OCR, right? And then also Zola gave a talk about, while it was more specific to languages, but he did make mention of the fact that besides templating, other techniques that have been employed manifest themselves in the shape or form of taking deep learning approaches by making use of so-called neural networks, right? And then, of course, my talk, previous talk, was centered around document classification, really classic case of supervised machine learning. Now, I didn't include Nock's talk here because I think the time I was preparing the slides was slightly before the talk by Nock, but key thing here is Nock's talk was classic and supervised machine learning. All right, I hope this brief walkthrough here will help us gain or help us get started in appreciating the different types of machine learning techniques that are out there that can be taken advantage of to try and make sense out of data. Fundamentally, what we are doing in all these different examples we've been citing is we're trying to make sense out of data. Different types of data, text data, right? Images, right? But fundamentally, we're interested in patterns. All right, so in the next part of the lecture series, we're just going to walk through model evaluation. I'm just going to pause for now.